Last time, we were introduced to the science of organic chemistry, and we saw how just two elements, carbon and hydrogen, can combine to create a vast array of stable molecules. We call these molecules hydrocarbons. And we learned how to think in terms of carbon scaffolds capped with hydrogen atoms. But what we didn't consider is that hydrogen isn't the only element that can bond to carbon chains. Many of the other elements, particularly other nonmetals, bond to carbon well enough that they too can become features in organic molecules. So during this lecture, we're going to invite some new attendees to the organic chemistry party. Some of the most frequently encountered guests are nitrogen, oxygen, sulfur, phosphorus, and the halogens. But that list is by no means exhaustive. Now, in this lecture, we will just begin to explore a few organic molecules that contain some of these elements, and we'll see how their properties differ from hydrocarbons and from one another. When any element other than carbon and hydrogen is present in an organic compound, we call these new additions heteroatoms. The inclusion of heteroatoms has a few very special effects on organic compounds. First, the inclusion of more electronegative elements like nitrogen, oxygen, fluorine, and chlorine, for example, can introduce bond-level dipoles into molecules, creating classes of compounds that contain polar bonds. Now, as you might imagine, the presence of these polar bonds can have dramatic impacts on the physical properties of a compound. They can do this by introducing the possibility of molecular polarity, varying levels of acidity, and even hydrogen bonding. Second, more complex geometries and even more isomers become possible as heteroatoms like nitrogen and oxygen can not only replace hydrogen atoms in hydrocarbon frameworks, but extend and sometimes even branch chains themselves. These two factors in combination create a truly massive library of remarkably diverse compounds, one that dwarfs even the staggering inventory of possible hydrocarbon structures that we discussed last time, both in size and complexity. Indeed, the inclusion of heteroatoms into the discussion gives us a virtually endless supply of potential compounds to study. Although many elements have a role to play in organic chemistry, today we're going to focus on the most common heteroatoms encountered in organic chemistry: oxygen, nitrogen, and the halogens. Halogens are a great place to start considering what happens when we really open up the periodic table to organic chemistry. This is because halogens, just like hydrogen, typically form only one bond, capping off one bond in a carbon scaffold. When we replace one or more hydrogens with a halogen, we call the new molecule an alkyl halide. Alkyl for the alkane we started from, and halide to indicate that at least one halogen has replaced a hydrogen. Rigorously, in organic chemistry, we often call this halide on an alkyl halide a substituent rather than a functional group for reasons that we'll discuss a bit later. For now, it's worth mentioning because IUPAC nomenclature treats halogens just like alkyl groups. So when naming alkyl halides by this convention, we follow the exact same method that we did in our last lecture. For example, this molecule would be called 1-chloropropane, and this one 2-chloropropane, this one 2,2-dichloropropane, and so on. Now take the example of methane. Here are a few methyl halides, or alkyl halides created from methane. Some of these should seem familiar. Chloromethane and dichloromethane are compounds familiar to most chemists, but not generally recognizable to the average person. Chloromethane found use as an early refrigerant, and dichloromethane was once a commonly used solvent employed in, among other things, the decaffeination of coffee. But add some more chlorine and you get some very familiar sounding names: chloroform, carbon tetrachloride. These two solvents have been used in dry cleaning and other industrial processes, and are both probably somewhat familiar. Notice that when it comes to alkyl halides, the carbon backbones are essentially unchanged, but halogens themselves are bigger, in some cases much bigger than hydrogen atoms that they've replaced. They're more electronegative too. And this means that when we start replacing hydrogen atoms with halogen atoms, we begin introducing larger electron clouds and some new polar bonds that weren't there before. This can have a profound impact on the physical properties of an organic compound, and no story demonstrates it better than that of Thomas Midgley Jr. American chemist Thomas Midgley might be one of the most infamous chemists of all time. For most of his career, Midgley was in the employ of General Motors as a researcher. Now, in the 1920s, he was working for the Frigidaire division of GM, and it was his job to find and create new materials to improve the lives of the customers of GM. Unfortunately, it turns out that by no discernible fault of his own, Midgley managed to find himself the creator of one of the most infamous compounds in human history. Midgley created this, Freon 12. Notice that Freon is really just a methane molecule, but with its hydrogen atoms replaced by 2 chlorine atoms and 2 fluorine atoms. Midgley created this compound because it had the very desirable properties of a refrigerant. It had a much higher boiling point than ethane because of the van der Waals dispersion forces and dipole-dipole attractions that stem from those large polarizable and electronegative halogen atoms that he added. Many other versions of Freon were subsequently created, each an alkyl halide consisting of a carbon backbone with various amounts of fluorine and chlorine in place of some or all of its hydrogens. This has led to the now frequently used term chlorofluorocarbons, which refers to this entire group of organic compounds collectively. It also turns out that Freon 12 and other chlorofluorocarbons are not flammable, which, believe it or not, was an improvement over early refrigerant designs. Prototypical refrigeration units from the late 1800s were prone to explosions caused by the highly flammable refrigerants in use at that time. Freon is also not toxic to humans, so a leaking refrigerator compressor became a much less serious safety and health hazard. So we'll give Midgley a moment in the sun today for his role in introducing the world to Freon. But he's going to be back a bit later when we get to our lecture on atmospheric chemistry, and his story isn't going to be so uplifting. Midgley wasn't the only one to look to alkyl halides for a stable material for use in engineering. Not by a long shot. Alkyl halides like perchloroethylene, originally synthesized by Michael Faraday himself, were a curiosity in the 1800s, but are now commonly used in dry cleaning processes because they're fairly non-reactive and can solvate the low-polarity materials that make up most clothing stains. Remember our rule that like dissolves like. Here it is in action. Oxygen is a very common element. That's good news for us, because in its pure diatomic form, oxygen provides us with the means of tapping energy as bonds of other molecules interconvert via combustion. Right? Your car needs it to burn octane for energy, and you yourself need it to oxidize other fuels like sugars, fats, and proteins in the foods that you eat. But once it reacts with organic material like hydrocarbons, oxygen isn't done. In a complete combustion reaction, we depict oxygen reacting with a hydrocarbon to become carbon dioxide and water. This is the ultimate product of the reaction, true, but more controlled oxidation reactions can lead to new organic materials that contain oxygen. Let's take a look at a few of those. All right, our goal now is to take one of those hydrocarbons that we discussed previously. Let's take ethane and add oxygen to it, but instead of doing so as we might in a combustion reaction where we simply add as much oxygen as we possibly can, essentially obliterating the molecule, and instead add that oxygen atom by atom, bond by bond, forming new organic molecules. In the first step, we're going to take our ethane molecule and we'll add 1 oxygen. The simplest way to do this is by placing the oxygen in a single bond to one of the carbons, and of course it's going to need a hydrogen to cap it off as well. This is a molecule of ethanol, an alcohol. And we call this OH group here a hydroxyl group. So you'll hear me use that term from time to time to describe an OH motif that is bonded to an organic molecule. But we're not done there. We can add additional oxygens or additional bonds to oxygen in several ways. The first of which is we simply create a double bond to the oxygen. Right? We have to remove 2 atoms of hydrogen from our molecule to do this. but we've added a new connection to the oxygen, so we would say that this is more oxidized. This molecule is known as acetaldehyde, and it contains what we call an aldehyde group, which is a carbon double bonded to an oxygen and also singly bonded to a hydrogen. But we can go even further. We still have additional connectivities here that we have not yet used to put oxygen on the molecule. Let's put another one on. When we put another oxygen on, we add a new hydroxyl, creating an overall group known as a carboxylic acid group, because this hydrogen right here is actually fairly acidic. It's removed somewhat easily. But as you can see here, we've added yet another oxygen atom and yet another bonds to an oxygen atom. So we would say that ethane can be oxidized into ethanol, which can be further oxidized to create acetaldehyde, which can be even further oxidized to create the carboxylic acid, acetic acid, which we sometimes call vinegar. But as we add additional carbon atoms to our molecules, things become even more complicated. And we can illustrate this by adding just one more carbon to the equation. Let's consider propane. Now, when we oxidize a molecule of propane, we have to ask a new question. Which one of the carbons gets oxidized? Because all the carbons are not created equally here. Notice that there is a terminal carbon, but there's also a carbon there in the middle, right, that's bonded to two other carbons and therefore is in a distinct chemical environment. So when I oxidize propane to make propanol, there are two possibilities. What we call N-propanol, or normal propanol, in which our hydroxyl is on the end carbon, but there's also the possibility of putting the hydroxyl here on the central carbon. And we would call this molecule isopropanol, meaning same as propanol, although obviously these are not exactly the same. These are isomers of one another. Further oxidation, we have to ask the same question. Do we want to put our carbonyl on the end or in the center? It makes a very important difference chemically. When the carbonyl is on the end, we call this a propanal, or this is another aldehyde. But when we put it in the center and the carbon that's double bonded to oxygen has two other carbons, we call this instead acetone. Further oxidation of propanal leads me to propanoic acid, another organic acid just like we had when we oxidized ethane. But this highlights one of the important differences between propanal, which is an aldehyde, and my acetone, which is a ketone molecule, we call it. And that is that we can't oxidize this any further because the carbon is not connected to any hydrogens that I can remove to accommodate that new hydroxyl group. So the end of the oxidative chain when I'm working with the central carbon is actually acetone, whereas the end of the oxidative chain when working at the end of the molecule would be a carboxylic acid. So again here, when I oxidize propane, I have to consider where do I put the hydroxyl to get N-propanol or isopropanol? And at that point, where do I put my carbonyl, my double bonded oxygen? Do I get propanal, an aldehyde, or do I get acetone, a ketone? And finally, if I'm dealing with a terminal carbon, I can get one more oxidative step to form what we call propanoic acid, a carboxylic acid molecule. Each of these classes of compounds has its own distinct set of chemical and physical properties that make it useful. Alcohols, for example, have a hydrogen bonded to their oxygen. This polar bond between electronegative oxygen and a hydrogen atom make the hydrogen slightly acidic. This property also gives alcohols the ability to donate or accept hydrogen bonds, a property which contributes to their versatility as solvents. Yet another interesting property of alcohols is their ability to hydrogen bond to other molecules of the same kind. Now, just like water, alcohols have remarkably high boiling points for their molecular size. Just compare the boiling point of ethanol at 78 degrees centigrade to that of propane, a similarly sized molecule, which boils at -42 degrees centigrade. The ability to introduce this remarkably strong intermolecular interaction into organics by inserting oxygen atoms has led to some very familiar products that we rely on today to improve our quality of life. Now, take this example. If one hydroxyl group has the effect of raising the boiling point of a material by over 100 degrees centigrade, what do you imagine might be the effect of two hydroxyls on the same molecule? Well, the answer to that question came in 1857 when a French chemist named Adolphe Wurtz first synthesized a compound containing not one, but two hydroxyls. The answer is just what you might expect. Compare the structures of butane, propanol, and a dialcohol sometimes called glycol. This is Wurtz's creation called ethylene glycol. All four molecules have nearly the same size and shape, yet the boiling point of butane is -1 degree centigrade. Propanol jumps to an impressive 97 degrees centigrade, and ethylene glycol, which is a hydrogen bonding machine, boils at a very high 197 degrees centigrade. It's exactly for that reason that ethylene glycol is used in automobile engines to help regulate heat. This very high boiling point liquid can be mixed easily with water to create a liquid with just the right properties to perform as an engine coolant. A bit of water to help reduce viscosity and increase thermal conductivity, and some ethylene glycol to be sure that the coolant itself doesn't boil under the heat generated by the engine, causing it to escape or damage the cooling system. This trend actually continues. Glycerin, a common ingredient in hand lotions, and also a precursor to the famous or infamous explosive nitroglycerin, contains 3 hydroxyl groups. This makes glycerin a perfect choice as a base for lotions or creams that you don't want evaporating quickly. Mix a few nice-smelling compounds in solution with glycerin, and the pleasant effects of applying it to your skin will last for hours. Now let's take another step down the oxidation chain. Our next step changes the oxygen slightly by double bonding it to the carbon, creating carbonyl groups. Now, switching out an alcohol for a carbonyl changes the properties of a compound in some pretty profound ways. When we substitute a carbonyl in place of a hydroxyl, we get one of 2 new functional groups. Placing a carbonyl at the end of a carbon chain creates a class of compounds known collectively as aldehydes. Doing so within a chain creates what are known as ketones. Now, aldehydes and ketones differ dramatically from their alcohol counterparts in 2 critical ways, so let's explore those. Here are 2 familiar carbonyl compounds, propanal and acetone, those 2 carbonyl compounds we looked at in a previous slide. Now, what I'd like to call your attention to right now is these lone pair electrons on the carbonyl oxygens. This means that they have the potential to hydrogen bond, but they don't have a hydrogen of their own to donate to the hydrogen bond. So what this means is that they actually can hydrogen bond fairly well with other solvents that do have that hydrogen, solvents like water. So we see propanal and acetone, although they're organic molecules, dissolving fairly well in water. But what really sets them apart from alcohols is that they can't hydrogen bond to themselves. Here's isopropanol, one of our earlier molecules. And when I bring 2 together, as you can see over here, I can very easily arrange them in such a way that they hydrogen bond to one another. But acetone, on the other hand, lacks that important OH bond in order to donate a hydrogen bond. It can only receive them, which means that other acetone molecules simply can't have this kind of interaction with one another. And this affects their phase behavior dramatically. However, think about this. Carbon-oxygen double bonds contain a pi bond, which are generally weaker than a sigma bond. What that means is that carbonyls have a tendency to be more reactive. So rather than using them as, for example, solvents where we don't want them to react, we frequently use them in situations where we do want them to react. Like formaldehyde, which actually reacts with water to create a molecule with 2 hydroxyl groups. This is actually the active version of formaldehyde that undergoes the reaction that preserves biological tissue. It's not the formaldehyde itself, it's the product of its reaction with water. So this lack of ability to hydrogen bond to themselves, but their increased ability to react with certain things, actually leads to a very different class of compound when we're talking about ketones versus alcohols. To find evidence of carbonyl's inability to hydrogen bond to themselves, we have to look no further than the boiling points of the simplest examples of these compounds. Methanol, sometimes called wood alcohol, has a boiling point of 65 degrees centigrade. Now compare that to the boiling point of formaldehyde, a carbonyl-containing compound of similar size. Pure formaldehyde boils at a chilly -19 degrees centigrade. Well, this might sound surprising since most of us are familiar with formaldehyde as a liquid used to preserve biological material. In truth, the formaldehyde that we use for this purpose is a solution of formaldehyde dissolved in water. What makes formaldehyde useful as a preservative is its ability to react with complex proteins within the biological material that it permeates. The key to this reactivity involves the breaking of the weaker pi bond to the carbonyl oxygen, which begins a series of chemical reactions in which the formaldehyde chemically bonds proteins in tissue samples together, and this slows their decomposition. Our final stop on the journey of oxidizing organic compounds is here, the carboxylic acid. Now, we live in a very oxidizing environment, so you might not be surprised to find out that carboxylic acids are some of the more common and longest known organic compounds known to man. Carboxylic acids include some very familiar compounds, like the formic acid that produces a burning sensation when you're bitten by a fire ant, or the vinegar used in cooking and pickling. Others we come into contact with often but might not even think about, like the propionic acid used as a bacterial growth inhibitor in feedstocks, or the somewhat unpleasant, acrid-smelling butyric acid produced naturally by bacteria in the butter-making process. All of these compounds and many others fall into the class of carboxylic acids because of the functional groups that they possess. Notice that carboxylic acids essentially can be described as a compound in which both a carbonyl and a hydroxyl are attached to the same carbon. This makes carboxylic acids remarkably versatile compounds. The presence of a hydroxyl gives them the ability to hydrogen bond to themselves, while the presence of the pi bond in the carbonyl gives them a certain desirable reactivity in some cases. Now, not only do carboxylic acids find use in a broad array of products from flavorings and preservatives like vinegar and benzoic acid, but also as the starting materials in processes that create new useful compounds, from drugs to perfume additives. Our third and final heteroatom for this discussion is nitrogen. Making up 78% of our atmosphere, nitrogen is quite literally all around us in its pure molecular form. Now, it also makes up about 3% of the mass of your body. That may not sound like much, but the role played by that nitrogen cannot be duplicated by any other element in the universe. Many of the nitrogen-containing compounds in our bodies are very large, complex biomolecules, like the proteins making up your muscles and the wide variety of enzymes catalyzing reactions in your body that are keeping you alive right now. For evidence of the presence of nitrogen in living tissue, you don't need to look any further than your own nose. Any of us unfortunate enough to experience the smell of decaying flesh had detected nitrogen-containing organic molecules. In fact, it was from that very source that some of the first nitrogen-containing compounds were isolated. They have the rather unappealing names putrescine and cadaverine. Those are an homage to the grisly source from which they were first isolated. Nitrogen has certain similarities with oxygen. It's relatively small, somewhat electronegative, and fairly abundant in the environment. But it also has some distinctions. Most notably, it readily forms 3 bonds per nitrogen atom, compared to oxygen, which typically forms 2. This gives nitrogen the ability to form a much broader array of possible bonding arrangements, too many to cover in a single lecture. Instead, I'm going to focus on the simplest, and in many cases, the most common nitrogen-containing organic compounds. During this lecture, we're going to take a look at a class of organic compounds called amines. Nitrogen is extremely abundant and totally essential to life as we know it. But it can be tough to come by in a form that an organism can use. We already know that. Diatomic nitrogen is joined by a triple bond. That's very difficult to break apart because the triple bond itself is very, very strong. Now, breaking this bond to get the nitrogen atoms inserted into an organic compound is exceedingly difficult. But thankfully, a few very special bacteria have the ability to break molecular nitrogen down, combining it with hydrogen to form the compound ammonia. At this point, we can see how nitrogen in ammonia is bonded to 3 different bonding partners, all hydrogen atoms. Of course, ammonia is not truly an organic compound by the modern definition because it has no carbon atoms. But unlike nitrogen gas, which is practically inert, ammonia can react with organic compounds, inserting itself into the realm of organic chemistry and taking on connections to carbon in lieu of hydrogens. Now, amines consist of, essentially, a nitrogen atom that is chemically bonded to what we call an R group, or some kind of a carbon-containing organic motif. But remember, nitrogen can have up to 3 different single bonds. So we have a situation where we can have compounds that contain nitrogen with 1 R group, 2 R groups, or even 3 R groups, in which case we call them primary, secondary, and tertiary amines. Here are some simple examples. Methylamine has 1 R group and therefore would be considered primary, whereas dimethylamine in the center here has 2 R groups and would be considered secondary, and trimethylamine, which has all 3 bonds to the nitrogen as R groups and none of them as hydrogens, would be called a tertiary amine. And the number of bonded groups to the nitrogen can have a profound effect on how these compounds behave, both physically and chemically. Primary and secondary amines differ from tertiary amines because they have NH bonds, which allow them to hydrogen bond to one another, raising their boiling points. For example, the primary amine propylamine has a boiling point of about 50 degrees centigrade, whereas trimethylamine, a tertiary amine, has a boiling point of just 2.9 degrees centigrade. Same elemental composition, but very different volatility. This is particularly unfortunate if you're standing over a piece of fish that is less than fresh, since trimethylamine is a byproduct of decomposing of fish in particular. Its inability to donate hydrogen bonds allows it to enter the vapor phase more easily as it forms, helping it to get from that fish to your nostrils. There are, of course, those who would argue that this isn't unfortunate at all. In fact, as animals, we've evolved specifically to have strong repulsive reactions to small quantities of these kinds of amines. This is a protective mechanism that prevents us from consuming unsafe food that could harm or even kill us. So far, we've considered just a few of the elements that combine with carbon and hydrogen to form a versatile and virtually unlimited library of organic compounds to explore. But imagine this. We still have not considered the more than 100 other elements and what roles they can play in changing how a scaffold might react. And we also have yet to carefully consider functional groups that contain more than one type of heteroatom, like amides and amino acids. Now, these both contain oxygen and nitrogen atoms. There are even a class of compounds called organometallics, in which a variety of metals from lithium to iron to copper and many others combine with organic compounds to make even more complex and varied chemistry. We could create an entire course in itself to cover the vast array of potential heteroatoms in organic chemistry and the roles that they play in this critical class of materials. But for now, the rest of our course beckons, so we better sum up. We started by acknowledging that there's more, much more, to the world of organic chemistry than just hydrocarbons. We acknowledge that just about every element in the periodic table can play a part in the chemistry of carbon-based compounds. But we decided to keep it simple and consider just halogens, oxygen, and nitrogen, and the roles that they can play in tuning the chemistry of organic compounds. When we focused on halogens, we noted that they only tend to form one bond, so they terminate chains just like hydrogen. However, we also saw how their high electronegativities and large electron clouds can dramatically change their physical properties, a fact that Thomas Midgley exploited in the development of Freon 12. Next, we invited oxygen to the party. We saw how oxygen's ability to make 2 bonds makes its role in organic chemistry even more complex and impactful. We saw how hydroxyl groups and carbonyl motifs can create a number of different functional groups with widely varying boiling points, acidities, and reactivities. Then we considered nitrogen's role in organic chemistry, focusing just on one of the simplest examples of nitrogen-containing motifs, the amine functional group. We saw how nature has to work hard to get nitrogen into the biological world because of its high stability in the diatomic state. But then we saw how dramatically different amines can behave, and particularly how dramatically different they can smell. Finally, we took just a moment to consider how much more complex the world of organic chemistry can become when you combine nitrogen and oxygen in a single organic molecule, or when you open up the rest of the periodic table to participate. So during this talk, we developed an appreciation for the structural complexity of organic compounds and how those structures affect their physical properties in particular. Next time, we're going to take our discussion to the next level and consider not just how organic compounds behave in and of themselves, but how they can react with one another to drive the processes that support life and the processes that help us to improve our lives. Next up is our lecture on organic reactions.